Right, in this video we are going to talk about electromagnetic waves. So everyone knows, you're probably familiar with stuff like light. You're kind of not going to be familiar with light if you're watching the YouTube video. And light is just an electromagnetic wave, and it's part of a small band of the full electromagnetic spectrum. So we're going to talk about this. So the first one is radio waves, and these are the weakest, the lowest energy waves of the whole electromagnetic spectrum, and they have wavelengths of 10 to the minus 6 meters to 10 to the minus 1 meters, and these are kind of like all arbitrary sort of ranges that we sort of like put on them. Sort of, someone's not. They kind of like different textbooks will say different things, but that really doesn't matter as long as you just have sort of like long ones. They're radio waves, the really long ones, and the sort of uses of obviously for radio, where we sort of listen to our music and stuff, and TV. They're mainly communications based, and that's what sort of radio waves are for. So these have the longest wavelengths of all the sort of electromagnetic radiation, and as such the lowest frequency and therefore the lowest energy. So the next one are microwaves, and these range from 10 to the minus 1 to 10 to the minus 3 meters. So they're sort of like the next one along. Microwaves, we have uses obviously for cooking food, again for communication. That's how sort of your phone works. Just, you know, they're pretty much, it's kind of like similar to radio waves obviously, but microwaves have more energy because they have a higher frequency and a lower wavelength than radio waves, so they can be used for like slightly different things, such as cooking food. You can't cook foods with radio waves. You could, but it'd take absolutely ages, and that's, you know, obviously not what everyone wants. So the next ones are infrared. So infrared are 10 to the minus 3 meters to 7 times 10 to the minus 7 meters. And obviously, like, this is kind of like a more specific number than this, and we'll see. I'll explain that in a minute. So infrared radiation is just pretty much heat. That's what it is. It's like any hot object will give off loads and loads and loads of infrared radiation. And again, like, this is used for cooking. Obviously, is heat. It's like kind of hard to cook stuff without heat, unless you're using microwaves. But yeah. So infrared, you use a source of infrared radiation is anything hot, but it can be also be used for stuff like your TV remote works on infrared radiation. So they can be used for communications over very short distances. So it's like it's just infrared radiation. It's kind of like think heat. You've got it. That's all you need to know. Now the next one is light, visible light, and this is where this comes into play. It's kind of like the specific range, and because it's the one that we can see, it's kind of like been the most studied by. It's kind of the narrowest band that we have to look at. It's kind of like we're sort of pretty certain of it because we know when it shuts off and when it's, because the definition is visible, so you can take the average amount that humans can see and sort of work it based on that. And obviously everyone knows what visible light is. How do you know if you've got visible light? Well, you can see it. It's pretty much it. And yeah, what's its uses? Sort of like seeing stuff or detecting stuff's coming your way. But you know, it's just it. Now the next one is ultraviolet. So UV light, or sometimes radiation. It's kind of like just your personal preference. And this is 4 times 10 to the minus 7 to 10 to the minus 8 meters. Now 4 times 10 to the minus 7 to 10 times 8 meters. UV light has some uses, as in terms of security tagging. So like, you know, you've got an expensive instrument like a violin, you sort of tag it with some special chemical that then when you pass it underneath a UV light, it will shine and sort of fluoresce and reveal the code so that if the police get your stolen violin back, God forbid that ever happen to you, something gets stolen, but this will help you if you mark it with that little UV sort of stuff that, it's not UV itself, it's like it shows up under UV light. Other stuff, sterilization, like your gadgets. You ever get one of those UV scanners, you can like pass your iPhone or whatever through and it'll kill all the bacteria on it. And tanning, sun tanning, or going to tanning salons or something, big UV lights and everything. There's some dangers with UV lights, as in all the other ones before. There's been some slight dangers, so like microwaves. There's been like news stories about like tumours from phones. Like none of it's proven, but none of it's not proven yet, so it's still a bit sort of iffy. Infrared, obviously, there's some dangers, kind of like if you put your hand in an oven, you probably want to go and take it out. You're not going to want to leave it in there for a time. Visible light, maybe if the intensity is too much, it can hurt your eyes, sort of thing. But ultraviolet, there is some real danger there. So, like if you spend too long sun tanning, UVC is the most strong. It's sort of like the shortest wavelength range of light, UV light, and it's the wavelength range that's blocked out completely from the ozone layer. So the ozone layer completely blocks out that one, so you don't have to worry about that. There's UVB, which lets some of it through, and this is the most dangerous one. So when you're out tanning, this is the thing that your sun cream is mainly blocking against and mainly absorbing and stopping reaching your skin. Because UVB causes genetic damage to the DNA inside your cells, which can lead to skin cancer, which obviously no one wants. No one wants skin cancer. It's just like bad. So that's the thing that sun creams are for, and that's why people wear sun cream. UVA is about 95% of the UV light that we have outside, and it causes tanning, and it can still cause skin cancer, but it's less likely to. And that's the sort of main contributor to the tanning, because it's the main one that we allow to have in contact with our skin. So that's just UV light. Now the next one, I'm going to clear some space here, is we have X-rays. Now X-rays go from 10 to the minus 8 meters to 10 to the minus 30. Now before I talk about X-rays, I'm going to just write down gamma rays, and you might notice something. So you have 10 to the minus 10 meters to 10 to the minus 16 meters. And there's an overlap. It's not a clear defined sort of thing, and it's not. It's kind of like an overlap between X-rays and gamma. It's not a it's like a clear shut-off point. So the way of detecting whether you have X-rays and gamma is by thinking first of how you've made it. So X-rays are made by bombarding metal with electrons, and that's how you get there. Sort of, they give off radiation by changes his electron shell orbitals, but you don't need to know about that yet. But stuff like that. Whereas gamma rays are from nuclear decay. So when an atom nucleus is splitting, it will release gamma radiation. So that's how you tell the difference between the two. And obviously, like 10 to the minus 16, if you kind of think, well, the radio waves sort of like stop there and they start. No, you can get longer than the radio wave range, and you can get shorter, more high energy, and it's sort of like sometimes called the forgotten zone or something. At least that's what my teacher calls it, the forgotten zone of electromagnetic radiation. Is things that are smaller than gamma. And it's just because they're so high energy that it's hard for us to make, so you don't really see them in your sort of like every day, and they're kind of like dangerous. You wouldn't want to like, for one thing, you wouldn't want to make gamma radiation in a class or anything. You wouldn't want to make gamma radiation in your house. You'd be kind of like worried if there was a source of gamma radiation. So anything more than that, you're starting to sort of worry a little bit. So that's why we don't sort of see them normally. But I can imagine that it's probably still called gamma radiation. It's just gamma just extends on, and because no one's sort of put the band there yet. So some uses of X-rays and gamma radiation are sort of like sterilization. They're good for that. Pretty much gamma can wipe out bacteria, and that's what we use it for. Medical imaging. So CT scans. Have you ever gone and had an X-ray? Surprise, surprise. It uses X-rays to get your bones. See on a picture. And also medical treatment. So cancer. is treated by using these two high energy sort of things to zap the cells and kill them, and that's pretty much the uses of X-rays and gamma rays. So now that we've known sort of the ranges and sort of the uses of them, let's sort of talk about what is an electromagnetic wave. What is an electromagnetic wave? Well, it is a transverse wave. It's a transverse wave, which therefore means it can be polarized. And that's one of the features of it. So let's go through some features of it. So we have features. Now, electromagnetic waves are transverse. We know this. So it can be polarized. Like all waves, it can be diffracted. We'll talk about that in another video. And it can travel in a vacuum. Travel through a vacuum. And that's kind of like one of the main sort of features of it. It's kind of like, how can it travel through a vacuum? It's a wave, it needs a medium. And like its medium is kind of like the electric fields and magnetic fields it goes from. We'll talk about that in a minute. So, and it can travel, when it's in a vacuum, can travel at the speed of light, which is noted c, and it is 3 times 10 to the 8 meters per second. Okay, so these are kind of like the main features of it. Now, what is an electromagnetic wave? We know its features, we know kind of like the ranges, but what actually is an electromagnetic wave? Okay, so this is just a little diagram I got off the internet to show you. Now, electromagnetic waves are oscillations in electric fields and magnetic fields, as the name would suggest. So, the electric field is shown here in red. Let me just highlight that. There you go. And this is perpendicular to this is the magnetic field in blue. So they kind of like go hand in hand, and when we're talking about, we just normally pick one or the other, because if you know one, you know the other. Just remember when you're drawing this diagram to include the labels. So we want the direction of the wave. We want to state which is the electric field and state which is the magnetic field. Doesn't matter which you choose to do, just make sure you label them both and show that they're perpendicular to each other. So like common questions asked are, what's different about electromagnetic waves from any other wave? Well, don't use transverse, because other waves can be transverse. So like a string, so, you know, the guy that we saw a few videos ago on a string making his wave is transverse. The special things about electromagnetic waves is they can travel through vacuums. They don't need that sort of like M molecules to transfer the energy, and so they travel really, really fast. They travel at 3 times 10 to the 8 meters per second when they're in a vacuum. Obviously, they travel a little bit much slower when they're going through stuff like air and everything, but kind of like they are the fastest things around. You can't go faster than an electromagnetic wave. So just sort of remember those things when the question comes up.